In this lesson, we are going to show you how to draw what are called Lewis dot structures, focusing on covalent compounds. Now remember, when things are making a bond in order to make a compound, there's a reason why they do this. And the whole goal of trying to bond is to try to get that octet. Remember, an octet is the most stable situation that an atom can have. It's why noble gases don't bond because they already have octets. So we find very, very, very few compounds that have noble gases in them. But everybody else is trying to get an octet. And remember, they can get an octet a couple different ways. And it all depends when two atoms decide to make a bond, it all depends on the strength of their pulling for those electrons. Or in other words, it depends on the difference in electronegativity. Now, we've already looked at what happens when we have an ionic bond, where we have a really, really big difference in the electronegativity. And so one of the atoms completely takes the electron from the other. Our keyword for ionic is transferred. So when we drew what we called the Madden equations before, we were showing how, in this case, the magnesium completely loses the electrons. That's how it gets an octet, and the oxygen completely gains. So now these electrons are permanently the oxygens now, and that's how it gets an octet. But in covalent bonds, as we said, the electronegativities are much more similar to each other. So there's a sharing involved. There's that pair of electrons ends up going back and forth. So our keyword is the electrons are shared. And this is what we're going to learn how to do today, is how to draw these Lewis dot structures, which show in a covalent compound how the electrons are shared among the atoms. So you can see in our example here, this is a compound called carbon tetrachloride. You can see that some of these have dashes, and that's what we call the structural model way of showing. And this dash represents that there is a pair of electrons that is being shared between this carbon and this chlorine. So it represents two that are going back and forth between the carbon and the chloride. So you can see we actually have four bonds, in other words, four covalent bonds in this molecule, where there are four pairs of electrons that are being shared between the carbon in the middle and each of these chlorines on the outside. So we'll show you how to do that. Okay, so how exactly do we draw Lewis dot structures for molecules, in other words, for covalent compounds? And remember, as we've just said, the whole goal is to get the octet. And since it is covalent compounds forming molecules, they're going to be sharing electrons to get their octet. So when we draw these structures, it's going to show the way these electrons, and they're going to be electron pairs that get shared. So we have our steps listed. This is our notes from our packets, probably around page 28 or so. And I have them written here. And we're going to go through and do an example as we go through these rules. So the steps are fairly easy. The first thing we want to do is simply draw the electron dot notation for each atom involved. So we're going to do this example here of selenium dibromide, which has a selenium and a bromine in it. And so step one just has to do the electron dot for each. So before we do our final answer for what the Lewis dot and structural model looks like, we always have to do some scratch work to figure out what these are. So I've labeled this scratch work. Now, a couple tips to help you out when you're doing your scratch work. Okay, we've got three elements to place in this molecule, three atoms, I should say. One selenium, and there's two bromine atoms. So the first thing we want to do is figure out just how do we want to line these up for our scratch work. And tip number one is to put the element that is more in the middle of the periodic table in the middle. And let me show you where the middle of the periodic table is. It might not be where you think it is. Okay, so the middle of the periodic table is actually right here. Okay, now you might be thinking, Mr. Arrow, you are bonkers. How is that the middle of the periodic table? That's obviously the middle. Well, if you think in terms of valence electrons, remember these guys all have 1 and 2, and mostly 2, and then 3, 4, all the way up to 8 valence electrons. The middle is 4. And so these guys are actually capable of making the most bonds because they have only 4 valence electrons. And so whoever is closest to this section here, put them in the middle, and then just surround them by all the other elements that you have. If you have hydrogens or any of these halogen guys, those are always going to go around the outside. So in this example here, we have selenium and bromine. So selenium is here, bromine is here, so selenium is closer to the middle. So what I'm going to do in my scratch work is I'm going to put my selenium in the middle and then just surround them by all the other elements. In this case, we've got just two other atoms, which are bromine, and so I'm just going to kind of circle. Doesn't matter exactly where you put them, but I'll just put my bromines around there. So that's step number one, is just to write down your atom symbols and putting your middle guy in the middle. Now, the next step is we need to continue doing the electron dot for each. So if we were doing selenium here, I want to figure out, well, how many valence electrons does selenium have? And I need to keep writing. Remember, that's really easy. You just count what column it's in to get the valence electrons. So selenium is in this column here, and everybody in this column has 6 valence electrons. Piece of cake. So around my selenium, we're going to do our 6 valence electrons. And remember, we always pair the first 2 together, and then we spread them out after that. Number 3, number 4, number 5, and then number 6. So that's my electron dot for selenium. Okay, now I want to do my electron dot for bromine. Of course, we can look at bromine on the periodic table and see that it's in column number 7. So it has 7 valence electrons around it. Now, another tip here for when you're doing your scratch work, when you're doing your valence electrons, is that you can rotate your electrons. And when you do the electron dot, sometimes you've got pairs and sometimes you've got unpaired electrons. You know, if we look at our selenium, we can see here's some pairs of electrons, but it has 2 unpaired electrons. So a good trick is to rotate your electrons so that any unpaired electrons you have are towards the middle. Now let me give you an example of what I'm talking about for this. Let's say we're looking at oxygen. Okay, so oxygen has, we can look again, make sure you've got this down. It's got 6 valence electrons. So if we were going to do it, normally we've always put the first 2 together over here on this side, and then we've gone 3, 4, 5, and now we start to double up, 6. So we've drawn the structure for oxygen that way. Okay, and looking at it, we can see that oxygen has 2 pairs of electrons. There's a pair and there's a pair. And oxygen has 2 unpaired electrons. There's this unpaired one here and this unpaired one here. Now, atoms are three-dimensional, so they can spin and they can rotate. So we don't have to draw everything exactly this way. So if I were to draw my oxygen like this, there's my 6 valence electrons. Hopefully you can see how we've just rotated it around. You notice we still have 2 pairs and 2 unpaired. So that's a perfectly acceptable way to draw oxygen. It's really the same thing. If we look at this example, again, there's 6 electrons, there's 2 pairs and 2 unpaired electrons. Would this structure be an acceptable way to draw oxygen? Of course, the answer is no, because even though we have 6 electrons here, in this case we have 3 pairs and 0 unpaired, so that is not an acceptable way. Okay, so you can rotate it however you want to, but you've always got to have 2 pairs and 2 unpaired. So our trick is to always rotate them to put the unpaired ones in the middle. So in this case, we're trying to do bromine, and so if we think about, well, what would the structure for bromine look like? Well, like we said, it has 7 valence electrons, so normally we would go 1, 2, 3, 4, 5, and then go back and double up 6, 7. So we would traditionally draw bromine this way. We can see it's got 1 unpaired electron, so we could also draw bromine, we could put that unpaired electron on the bottom if we wanted to, and draw it this way. So what I like to do when I'm doing my scratch work is to take my bromine, and it's got this 1 unpaired, and I'm going to put it towards the middle. Okay, so in this case, I'm going to draw my bromine with that 1 unpaired electron here, and then I'll draw my other 3 pairs around it the other way. And this one, I'm going to rotate this toward the middle. I didn't draw this very well here. I didn't give myself a lot of space, but then here's my 3 other pairs. So that will usually make your life a little bit easier if you draw things that way. So the next step is we now have to show how they're sharing electrons, okay? Because they don't have octets right now. They're not going to transfer because their electronegativities are similar. So they're going to share, but they can only share the unpaired electrons. So this is your chance here. Now, those of you that like to play Cupid with relationships and try to match people up, this is your chance here to play Cupid now, because what you want to do is pick any unshared electron or unpaired electron. Okay, these guys here are already paired, so leave them alone. Don't mess with them. But this bromine has one unpaired electron, and let's play matchmaker here. Let's pair that one up with that one. Okay, so we've now paired those unpaired electrons, and then we can do the same thing over here. Let's pick another one. Here's another unpaired electron, and there's only one other choice to pair it up with. So again, we're just going to do the scratch work. I like to draw circles around these just to show who we're matching up with who. Okay, so that would be our scratch work for this. It's not our final answer. So to draw our final answer, what we want to do is start with your atom that you had in the middle. In this case, we had our selenium atom in the middle, and do the pairs, because we didn't do anything with those pairs. So I always draw those first. And then when I'm by circling these two electrons, what I'm saying is that bromine is going to share this electron and selenium is going to share this electron. So these two electrons are going to be going back and forth between the bromine and the selenium. So what I'm going to do is just, I'm going to draw this electron on top and kind of just tractor beam this bromine in up here and draw this electron from the bromine. I didn't give myself much space here. Sorry, this is not pretty. And then show that this pair here now is going to be shared between the selenium and the bromine. This represents our circled pair. Now, of course, bromine had these other three pairs that we didn't do anything with. So I have to draw those other three pairs. Hopefully you can see that. Okay, around that bromine. And then we do the same thing here. Okay, selenium had this one electron on the side, and it's going to share it with this one from the bromine. So we're just going to kind of tractor beam this bromine in here. Okay, there's my pair now that I had circled, and we're going to draw the bromine over here. And then my bromine had these three pairs that we didn't do anything with. And so we'll draw those three pairs in like that. So sorry, this is pretty ugly here. But there is our Lewis dot structure for this. Okay, now remember the whole reason in bonding was to be more stable. So before we say, yep, I'm done, we always want to ask ourselves what I call two check questions. Okay, check question number one is, does everybody have an octet? Remember, that was the whole goal in bonding. So let's look at our structure. Does everybody have an octet? In other words, does everybody have access to 8 electrons? So if we look at this bromine here, we can see it has these 6 electrons, which we didn't do anything with. Now, even though these 2 electrons, this is our shared pair, they're going back and forth, the bromine does have access to those 2 electrons. So yes, this bromine has access to an octet. Okay, the selenium, again, had these 4 that it already had around it, and it's sharing this pair, and it's sharing this pair. So yes, the selenium has access to an octet. And this bromine on top is the same as the one on the side. It has its 6 plus its pair that's being shared. So our answer to check question number 1 is yes, everybody has an octet. Okay. Now, check question number 2 is we need to make sure that we didn't create or destroy any electrons, because we're not allowed to do that. So if we look in this example, the selenium had 6 valence electrons, so it brought 6 in, and your bromine each had 7 valence electrons, so we had 7 times 2 was 14. So we should have a grand total of 20 electrons. Okay, we cannot have any more than 20. We cannot have any less than 20. You can't just destroy or create electrons out of thin air. So if we check our structure here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so if your answer is yes to our 2 check questions, everybody has an octet, we've got the right number of electrons, and everybody is connected, then you know you have the correct Lewis dot structure. Okay, now what we often draw instead of the pure Lewis dot is a structural model, which is really the same thing. It's a lot faster to draw, and it looks a lot better, especially compared to what I've done here. So if I'm drawing my Lewis dot, I'm going to again start with my guy in the middle of the selenium. And since this pair is being shared, this is where we draw that with those dashes that we saw earlier. So selenium is going to share one pair with this bromine up top, and selenium is going to share another pair with this bromine on the side. Now, of course, you always want to draw all of your electrons. So I've got to draw my other dots. Those are two separate dots. They kind of bled together there. And then bromine has the three pairs that it had around it. And then my selenium had those two pairs we didn't do anything with. So this would be my final answer for my structural model. This would be my pure Lewis dot. We usually draw this because it's a little faster to draw and it shows the bonding much more clearly. And so that would be our answer for that. So that's how we do that. Okay, so on the bottom of your page, I have a few examples that I want you to try, and then we'll go over them. Okay, so just going over our answers to these. First one was H2S. So again, since S was in the middle of the periodic table, I put sulfur in the middle and I just surrounded it by the hydrogens. I put my 6 valence electrons around it. Hydrogen only has 1. So now we play Cupid. I pick any unpaired, pair them up. Now, just about the only rules for playing Cupid here is you cannot pair two unpaired electrons that were on the same exact atom. So for example, if I had chosen this unpaired one at sulfur, I cannot pair it with this one on sulfur. Okay, so, and even if I did that, then there wouldn't be any way for me to connect everybody else to the sulfur. So I would come to a dead end even if I did it that way. And sometimes that happens, when you're playing around here. So pencil and eraser is always a good way to do this. If you come to a dead end, then just erase what you've done and try a different combination of pairing things up. Okay, so there is a little bit of playing around with these. Some of them get a little harder. But anyway, I decided to pair these two up and then just keep going. Okay, you've got to keep going until everybody is paired up. And so I'll pick this one. Not a whole lot of choices here. Those are the only two left. And so that will be my scratch work. So I've got all of my electrons paired. So when I go to draw my Lewis structure for that, I just basically showed my pair that was shared. I drew them between the H and the S. So remember, that's what that represents. And then here's my pair here that's shared. Okay, and there's my final answer. Again, just to make sure that I'm like that answer, there's my two check questions. Does everybody have an octet? And we can see that, yes, the sulfur has access to 8 electrons. Now, the hydrogen does not have 8 electrons around it. It only has 2. But remember, for hydrogen, that is its version of an octet, because hydrogen only has 1 energy level. And remember, it only takes 2 electrons to fill the first energy level, because all you have are s orbitals. There's no p orbitals on the first. So with sulfur having just 2 electrons around it, that's kind of its, there's my quotes, its octet. Okay, so hydrogen is good, and everyone's happy now because they all are very stable. And of course, my next question is, do we have the right number of electrons? Hydrogen each had 1 valence electron. Sulfur had 6, so 6 plus 2 is 8. Check my structure. Do I have 8 electrons? Yes, I do. So thumbs up, we know that's good. Okay, and then finally, the cleanest way to draw that, the structural model, we just put the dashes anywhere we had a shared pair. Make sure you include all electrons, so make sure you're including these ones that were already paired up as well. Okay, so that was our H2S formula. When we go to do our next one, and this one was hard to fit in the little square here, I apologize for that. I did my scratch work. Phosphorus was the closest to the middle of the periodic table, so I put the P in the middle, and then I surrounded it with 3 of the Cls. Phosphorus has 5 valence electrons, so there's my 5 valence electrons around there. Chlorine just has 7, so I put my unpaired one to the middle when I drew this. And now again, we get to play Cupid. So just don't try to do too much in your head here. Just pick an unpaired electron. Like I said, if you come to a dead end, maybe you decide, okay, I'm going to pair this one with this one. Okay, well, if you do that, then there's no way to connect these CLs to everybody else. So everybody has to be connected. So if you come to a dead end, just pick it and pair it with somebody different. So maybe we decide, okay, let's pair this chlorine electron with that phosphorus electron, and then pick another one. Okay, I'll pick this one and pair that with that phosphorus one. And then those are my only two unpaired ones left. So do your scratch work for these. Now when I redraw this, again, draw your phosphorus in the middle. You should get something that looks like this. There's my pair that is shared between the Cl's and the phosphorus. Again, my two check questions. Does everybody have an octet? Do I have the right number of electrons? There's a lot of electrons here, but if you count the dots, you'll see that yes, everybody has an octet. And phosphorus brought in 5. Each chlorine brought in 7. So 7 times 3 is 21, plus 5 is 26. If we do a count here, we will see that yes, indeed, we have 26 electrons. So we can feel confident that is the correct structure. And just drawing the clean structural model version of this guy. Okay, there's our dashes there. Phosphorus is making single bonds to each of those chlorines. Okay, and finally, the last one, the H2O2. A little more interesting there because in this case, we've got 4 atoms, so it's hard to decide, okay, well, who's in the middle? So oxygen is closer to the middle of the periodic table, so I put my O's in the middle and then just kind of surrounded my O's with the H's. Now, maybe you drew one of the H's up on top. It doesn't matter. So I did it this way. Hydrogen only has 1 valence electron. Oxygen has the 2 unpaired. So again, when you go to do this, okay, pick an unpaired one. Again, if I connect this to this H, then I won't have any way to connect the H's to everybody else. So let's choose that one and we'll pair that one up maybe with this one from the oxygen. Now again, I can choose this. Here's an unpaired one. Now if I connect it to this one, now there's no way for me to pair up these other unpaired ones on the oxygen. Okay, remember you cannot connect 2 on the same exact O. So I'm going to pair this guy up with this guy on that oxygen, which leaves me 2 more that aren't paired. Now, even though these are both oxygens, they are on different oxygen atoms, so I am allowed to pair these guys up. Okay, so now, hey, we're done. We did a good job playing Cupid. Everybody's paired up. So when we go to clean this up, I actually did this backwards. I put it in the wrong space here. So here's my Lewis dot over here. I have this pair is being shared between the 2 oxygens. So I drew, here's my pair here being shared between the 2 O's. And then on the bottom of this O, I'm sharing a pair with the H. So there's my pair that's shared between that O and that H. And then the same thing on the other O, there's a shared pair that's being shared with that H. Don't forget to draw your unpaired your pairs that you already had that you didn't do anything with. So each O has these 2 pairs that it already had around it. So don't forget to draw those. And again, this is what my structural model would look like. Again, does everybody have an octet? The each O definitely has access to 8 electrons, and the hydrogen is good with its 2. So everybody's happy. And if we do an electron count, we should have 6 plus 6 plus 1 plus 1. So that should be 14. Do I have 14 electrons? There's 8, 9, 10, 11, 12, 13, 14. So we know we've got the structure correct. Now maybe you're thinking, oh, wait a minute, mine looks a little bit different than the way you have it drawn, Mr. Era. You could say, well, I drew mine this way. Well, that's the same thing. Let me show you here. It's a little different shape, and we're not exactly worried about shape for right now. We'll worry about shape a little bit later on. So as long as you have 2 O's connected to each other, okay, which we both do, and each O is bonded with 1 H, we're good. Okay, I'll consider that's the same thing. Okay, maybe you drew it this way. Again, you're okay. It's really the same thing. You've got 2 O's connected, and then each O has 1 H that is connected to it. So regardless of what shape you drew it in, we're not worried about shape for right now. That is good to go. So hopefully that helped you with drawing Lewis dots. In part 2, we'll take a look at some other scenarios that is really important for how to do this.